We've looked at intermolecular forces and talked about the different interactions that happen between molecules depending on the type of molecule we have. Now what we want to look at is some of the effects that those intermolecular forces have on their properties. Now in class I talked about the example of water, how water is a liquid at room temperature. It has dipole-dipole forces and hydrogen bonding, but also dispersion forces because everybody's got those. And H2S, which has just dipole forces and dispersion forces, no hydrogen bonding, and as a result it is a gas at room temperature and pressure. So we want to look at boiling points and melting points for liquids and solids because both of these things, boiling is going from liquid to gas and melting is going from solid to liquid, are affected by the ability to move molecules apart from one another. So we want to look first at vapor pressure. And vapor pressure is this pressure of the gas phase over a liquid sample. So if I took a cup of water, for example, and put a lid on it, and I measured it later on, what I would find is that there is some pressure of water molecules above that liquid water that are in the gas phase. If you've ever been to a gas station, especially in the summertime, it's very noticeable. If there's a puddle of gasoline on the ground, it evaporates very quickly, but you smell those gasoline molecules in the air because the interactions between those molecules in the liquid phase are very weak, and so it's easier, less energy required to move those molecules apart. If we look at something that has stronger intermolecular forces, say water, it's going to take more energy to get those molecules from the solid into the from the liquid into the gas phase, but it can still be done at room temperature, but it's not going to happen nearly as fast. If you had a puddle of water and a puddle of gasoline, all other conditions being the same, the gasoline's going to disappear a lot faster than that water. And so what we're breaking when we go into from the liquid to the gas phase is those intermolecular forces. Because remember, when we go from the liquid phase, there's still quite a bit of interaction between those molecules. And when we get into the gas phase, we've pulled those molecules apart, so there's virtually no interactions between them. And so the strength of the intermolecular forces tells us how much energy is going to have to go in to get a molecule into the gas phase. So as a result, when we have something that has low vapor pressure, so we have a very low vapor pressure, what we see is that it has very strong intermolecular forces, because what's going on is that those molecules are being held tightly in the liquid phase. There's strong attractions between those molecules. It's going to take more energy to move those molecules from the liquid phase to the gas phase, and as a result, very few of them can escape into the gas phase. Now, if I look at a substance with a high vapor pressure, say gasoline is a perfect example of this, we have very weak intermolecular forces. It doesn't take a lot of energy to get those molecules from the liquid phase to the gas phase. So if I go back to my example of a puddle of gasoline, what I see is that it's not going to take too much energy to get those molecules to escape into the gas phase, and as a result, I'm going to get a lot of them to escape. So in the summertime, the temperature of the air is plenty warm enough to provide a huge source of energy to break those intermolecular forces. We're not breaking bonds. We're not breaking the intramolecular forces. Those are bonds. We're just breaking the attraction between molecules. Okay? And we have to overcome that to get molecules into the liquid phase. So if we have strong intermolecular forces, lots of energy needed to get molecules into the vapor phase, therefore we have a low vapor pressure. If we have weak intermolecular forces, it's easier to get molecules into the vapor phase. Less energy is required to overcome those attractive forces, and as a result, we have a very high vapor pressure. So let's look at an example here. Pause here to think about this question. Which type of molecules will have stronger intermolecular forces, polar or nonpolar? Hopefully you said polar. Remember that when we're dealing with something that's polar, it has our dipole-dipole forces, and it has dispersion forces. But when we look at nonpolar compounds, they are only going to have the dispersion forces. They're not going to have any other intermolecular forces. And we know that everybody's got dispersion forces, and they are very weak. And so polar molecules are going to have stronger intermolecular forces because we have these dipole-dipole forces present. So we know polar has these stronger intermolecular forces. So now let's look at the next question. Which type of molecules will have a higher vapor pressure? Polar or nonpolar? So pause the video here, take a minute to think about this, and then resume to hear the answer and explanation. Right. So we're looking for the substance that has the higher vapor pressure. And if we want something that has a high vapor pressure, that means that the molecules can escape very easily from the liquid to gas. So the liquid to gas is easy to do, okay, because it has a high vapor pressure. That means there's lots of molecules in the gas phase. So if we have lots of molecules in the gas phase, they were very easy to do, this phase change from liquid to gas. Therefore, we know that we have weak intermolecular forces because it doesn't take much energy to get that change to happen. Therefore, we're looking at nonpolar molecules. Again, going back to our example of the puddle of gasoline and the puddle of water. That puddle of gasoline is going to evaporate so much faster simply because the intermolecular forces between those molecules are much weaker than the intermolecular forces we see in water, and as a result, it's easier for those molecules to kind of acquire enough energy to escape into the gas phase. And remember, they get that energy from the temperature in the air. The temperature is just a source of energy, so the heat in the air will allow those molecules to escape. So high vapor pressure, easy for molecules to escape to the gas phase. We must have weak intermolecular forces. So we're looking at our non-polar compounds that have weaker intermolecular forces. So we looked at evaporation, which is one way of kind of creating the vapor pressure, of creating this vapor phase above a liquid sample. We can also look at this and say what happens when we heat something. And as we heat something, we're putting energy into the system, and so the vapor pressure continues to increase. We're still not at the boiling point yet. We're still just putting more molecules from the liquid into the gas phase. So we're still dealing with evaporation. At some point, we put enough energy in so that the vapor pressure equals the vapor atmospheric pressure. So when vapor pressure, so the pressure of those gas molecules above the liquid equals our atmospheric pressure, which for most parts of the U.S. is about 1 atm. So when the vapor pressure equals the atmospheric pressure, that is what we call the boiling point. So we like to talk about the boiling point as 100 degrees Celsius or 212 degrees Fahrenheit, and that is true, but it's only true at 1 atmosphere of pressure. If we change the pressure, what we see happening is that the boiling point will change as well. As the pressure goes down, so does the boiling point, because it's going to be easier to get to that vapor pressure. So we start with evaporation, and then we move into boiling. Both vaporization, both talking about the energy needed to get from the liquid phase into the gas phase. But remember, boiling point is when vapor pressure equals atmospheric pressure. Again, most of the time it's 1 atmosphere, but it doesn't always have to be that way. If we go out to Denver, for example, if you look on a package of pasta, it will tell you that you need to cook it a little bit longer when you're in the Mile High City. The atmospheric pressure is lower, and we don't need to be boiling to cook that pasta. We need this certain amount of energy, that certain amount of heat there. And if it's boiling at a lower temperature, we're not going to have as much heat from the water. So we've got to cook it a little bit longer to compensate for that lower temperature. But vaporization and boiling, evaporation and boiling are both forms of vaporization, liquid to gas. So what we see is that the intermolecular forces, not only do they affect the vapor pressure of a substance, but they're also going to affect the boiling point of a substance. If I have something with weaker intermolecular forces, I'm going to have a lower boiling point. So weaker IMF, I'm going to have a lower boiling point because it's going to be easier for those molecules to get from the liquid phase to the gas phase, less to overcome, and so it's going to build up that vapor pressure faster because the intermolecular forces are weaker and it's easier for those molecules to get to the gas phase. So every substance has its own boiling point, the point at which it is changing from liquid to gas, where the vapor pressure equals the atmospheric pressure. That's our definition of boiling. So let's compare some molecules here. We're looking at a couple of molecules. There's some alkanes here. So we have a pentane molecule here on the left, and we have a octane molecule on the right. And what we look at here is for the polarity, these molecules are the same. They're both nonpolar molecules, and they both have dispersion forces, but the amount of dispersion forces that they have is different. Because octane has more atoms, it has more electrons, and therefore it has stronger dispersion forces. And as a result, we're going to see that it's going to take more energy to get octane from the liquid phase to the gas phase, and that octane will actually have a higher boiling point than pentane does. So what we see is that if we look at these molecules, remember these are these straight chain alkanes, but what we have is a lot of interaction along the chain of these molecules. And so we see that these molecules are interacting in lots of different places, and in the octane they're interacting more than they do in the pentane. And so we have stronger interactions between separate molecules, therefore intermolecular forces are stronger, and the boiling point is higher. So let's look at an example here. Which molecule will have the highest boiling point? Remember what we learned about skeletal structures when we were talking about organic chemistry and what these symbols mean. So pause the video, think about it, and get your answer. So we're looking for the substance with the highest boiling point, and if I want the highest boiling point, then what I also want to have is the strongest intermolecular forces. Okay? Because if it has the highest boiling point, that tells me it's going to take the most energy of those molecules to get them in from the liquid phase into the gas phase. And the ones that are going to take the most energy to get from liquid to gas are the ones that have the strongest intermolecular forces. So when I look at the four molecules I'm given here, I notice that I'm dealing with four alkanes. So again, I'm not having to worry about dipole-dipole forces. I'm not having to worry about hydrogen bonding because I don't meet the definition of hydrogen bonding. It's not a mixture, no ion dipole, not an ionic compound, no ionic forces. All I'm worried about here are dispersion forces. And so what I'm really looking at is the difference in the molecular weight. These are all chain compounds. We'll look at the difference when we have branched compounds in just a second, but here we're looking at just the chain compounds. And so I look at the biggest one because it has the most atoms, therefore it has the most electrons, so therefore it has the strongest intermolecular forces. So it's going to have the highest boiling point. I can also look on the other end of this spectrum and say, well, what is going to have the lowest boiling point? Which one is going to take the least amount of energy to get from the liquid phase into the gas phase? So that's the molecule that has the weakest intermolecular forces, the ones that are holding on the least tightly to one another. And so what I can look at there is actually look at this smallest molecule. I only have 3 carbons in that molecule. Everything else has more. So that's going to have the lowest boiling point and the weakest intermolecular forces. And this is actually propane, so it's used as a fuel. It's usually in the gas phase until they put it in a canister under lots of pressure to force it into that liquid phase. So here's some examples of what we see for the boiling points of these alkanes. We start with CH4. We see a boiling point 161 degrees below 0 Celsius. And then we get to ethane. We see an increase in the boiling point. As we increase the number of carbon atoms in each of these alkanes, we see that the boiling point continues to increase. So the bigger the molecule, the higher the boiling point. However, note that we are looking at these as a set of alkanes. We're not mixing things. We're not dealing with what if I have a big alkane and a small polar molecule or a branched molecule. So it's kind of hard to predict things based on different classes of compounds, but because these are all the same basic compounds, or they're all the same class of compounds, it's much easier to make these comparisons about the boiling point. And so here we're given the actual values, but given the formulas or the names or structures, depending on which one's given, you should still be able to rank them in order of increasing or decreasing boiling point. So what happens when we deal with a branched compound? And so what we see is that the alkane here, the hexane molecule, it's straight, and like we showed in the picture of the pentane and the octane before, we had lots of interactions along the chain of the molecule between these different molecules, lots of alignment, lots of point of interaction for them. When I go to something that is branched, so 2,3-dimethylbutane, we still have the same chemical formula, the same number of carbon and hydrogen atoms. They're just connected in a different way, and so we actually have a structural isomer here. So we can't attribute differences in their boiling point to increased dispersion forces because they both have the same number of electrons. And so there's nothing different about polarity. They're both nonpolar, so no dipole forces. All we're looking at here is the connections between those atoms and the way the molecules are going to interact with one another. And in fact, it's going to take more heat to get the hexane into the gas phase. It's going to take more energy. It's going to have a higher boiling point than does the dimethylbutane, because when I look at how I would stack these molecules, there are not as many points of interaction between two molecules as I see in this hexane. So the more branching we see, the lower the boiling point, so less energy needed to get these molecules from the liquid phase into the gas phase. And when we look at the boiling point of that, we see that is the case. We see a lower boiling point for 2,3-dimethylbutane than we do for hexane because of a difference in the amount of interaction between the molecules. So again, going back to our example with H2S and H2O, we talked about H2O having these hydrogen bonds. So in water, we have our hydrogen bonding. Remember, it's not just hydrogens, and it's not actually a bond. We have our dipole-dipole forces, and we have our dispersion forces. When we look at our H2S molecule, we still have our dipole-dipole forces. We still have that polar molecule. We also have our dispersion forces here. And what we see is that there's a huge difference in the boiling point of these two substances. And that tells us that there's a huge difference in their intermolecular forces because the structures of these molecules, the shapes of these molecules are essentially the same. They're both this bent geometry. They both have two lone pairs. And in fact, sulfur actually has a few more electrons. If anything, we would expect the dispersion forces to be a little bit greater in the H2S. But remember, those are still very weak forces, so they don't, even having a little bit more there doesn't make a whole lot of difference. It's this hydrogen bonding in water that makes such a huge difference. And especially for water, because we actually have two hydrogens that are capable of interacting with that hydrogen bond to another molecule. And because we have two hydrogens that are eligible for hydrogen bonding, we actually see it hydrogen bonding to two other water molecules. And when we take all of these collection of water molecules and start putting and looking at how they arrange themselves and all these interactions happening, we actually make that kind of network of intermolecular forces very strong. And that's what explains this huge difference in the boiling point of H2O versus H2S. So what we look at here is we have to look first at nonpolar molecules. When we're comparing those, or any really class of molecules, even if I'm looking at polar molecules, if everything is pretty much the same except there's one little thing that's different, what I want to look at is the greater the surface area, the more points of contact that they're going to have. Alkanes versus the branched alkanes. The alkanes are going to have a much higher points of contact, more points of contact, and so they're going to interact with each other more, and as a result, their boiling points are going to be higher. If I look at different forces, the stronger the forces, the higher the boiling point is going to be. So we looked at H2O versus H2S. We can look at an alcohol versus an alkane. Any of those types of things, polar versus non-polar. And then we can look at molecules with the same forces. Then what we have to look at is which ones are going to be stronger, which ones are going to be more numerous, which ones are going to have more of. So we have to kind of look at multiple features, look at what the structure is, and look at how those molecules are going to interact with each other. For example, with water, we saw that we had two hydrogens eligible for hydrogen bonding, and so that's going to give us a lot more intermolecular forces, a lot stronger intermolecular forces than something that's only capable of forming one hydrogen bond. Now, all we've talked about here is boiling point, but here's the thing about boiling point and melting point. The trends are exactly the same. We don't see as dramatic a difference in boiling points and melting points between substances will have different polarities, but the trends are exactly the same. As I increase the overall strength of my intermolecular forces, I'm going to increase the boiling point, or the melting point, and the boiling point. Because remember, what I'm doing when I go from the solid to the liquid, that's what melting is. I'm going from solid to liquid. I've got to move those molecules apart from one another. They're packed in very tightly, and we're not breaking all of the intermolecular forces going from the solid to the liquid phase, but we are breaking some of those intermolecular forces. We've got to get that molecule or that substance to where those molecules can actually move past one another and as a result be in the liquid phase, because that's what defines us in the liquid phase, that molecules are capable of moving past one another. So everything we talked about boiling point holds exactly true for melting points. Temperatures are obviously going to be lower, but it's the same trend. So follow the exact same rules. And now you should be able to rank substances in order of increasing melting point or increasing boiling point, or reverse of that as well. If you have any questions on this, as always, please feel free to let me know. Come see me during office hours or post on Piazza.